All right, so picking up where we were last time, we started to just look at the concept overall of what organic and inorganic compounds were. And we talked about the primary differences between them being in their properties. The fact that organic compounds tend to be in the liquid and gas phases, whereas inorganic compounds tended to be a lot of solids. And if they were liquids or gases, they tended to be kind of the higher melting, higher boiling liquids and gases. Table 11.1 in your text gives a good kind of description of kind of where we can compare these to each other. And so in terms of elements, organic compounds are usually carbons and hydrogens. We also see oxygen and some of those other sponge elements in there as well. We also see some halogens in there from time to time. Whereas with inorganic compounds, I feel like we have to kind of quantify this. Most of the inorganic compounds that we're talking about are salts, because we're talking primarily about ionic kinds of compounds. And so while not every inorganic compound is ionic, most of them are. And because of that, we tend to see high melting points, we tend to see high boiling points, we tend to see relatively low flammability, because in order to burn, something has to be in the gas phase in the first place. And we tend to see solubility in water. And all those things in organic compounds, we rarely see. So if we just take a second here and kind of evaluate, we can look at these properties and pretty quickly identify them into one of the categories of either organic or inorganic. So if we know that we have something has a high melting point, that means that it's usually a solid. What kinds of compounds are usually solids? These would be the inorganics. The kinds of things that are not soluble in water, that don't dissolve, those would be the organics. If I see this kind of formula where I've got just carbons and hydrogens, that should be a sign that I'm talking about an organic compound. If I see combinations of metals and nonmetals, I know that's ionic, and ionic compounds are inorganic. The kinds of compounds that burn in the air are organic compounds. The kinds of compounds that are primarily covalent are also organic. So again, we know that some inorganic compounds do form covalently, but they're considerably less likely. Whereas it's pretty much impossible to think of an ionic compound that is also organic. There are a couple that exist. They are very rare, and they are used for very specific kinds of purposes that we don't usually get into. That's more in the material science kind of world. So let's look at the most common class of organic compounds. And these are what are called hydrocarbons. As you might imagine from the name, hydrocarbons, coming from hydrogen and carbon, these are substances that contain hydrogen and carbon, and only carbon and hydrogen. Here's where some of that information from chapter 6 becomes really relevant, though. If we look at carbon and we look at its dot structure, remember that carbon has those 4 unpaired dots. which means it's going to make 4 covalent bonds. And we see that in these organic molecules. Every carbon has 4 bonds. Now, in most cases, those 4 bonds are all single bonds. When we have only single bonds, we call those hydrocarbons saturated because they have as many hydrogens in their compound, in the formula, as is possible. If our hydrocarbon contains a number of double bonds or a triple bond, then we would call it unsaturated, because now it lacks some of the hydrogens that were present in the saturated form. So when we talk about this idea of saturation, when it comes to hydrocarbons, what we're talking about is hydrogen. Does the compound contain as much hydrogen as is possible? Because what we are going to see is that when these compounds form, the carbons, more often than not, are going to link up with each other like so. We refer to this kind of carbon backbone as the carbon chain. And when it comes to naming these hydrocarbons, identifying that backbone, identifying that longest chain is really the important part of trying to figure out how to name these things. So let's take a look at the simplest hydrocarbon. The simplest hydrocarbon would have just 1 carbon and 4 hydrogens. We call that compound methane. In methane, we see that we've got 4 carbon to hydrogen covalent bonds. They're all single bonds. Now you can get into this is some of the stuff that we skipped in chapter 5 and 6 about I guess it's chapter 6, about the shape of the molecule and how those bonds are angled apart from each other. That part isn't as important to us. But we need to understand that when it comes to organic chemistry, there are a number of different ways that we can represent compounds. So we're familiar already with just the chemical formula. We just write it out in order: element, however many atoms of that element, next element, however many atoms of that element, next element, however many atoms of that element, and so on. That's a chemical formula. But when we start to draw it out to try to get an idea of how it is put together, there are a number of different representations that we can use. We've already talked about these first 2. The electron dot formula, which is what we did in chapter 6, where you could see how those shared electrons link up with each other. The expanded structural formula, which is basically what we did to clean up the Lewis dots, so that was a little bit easier to see how they were put together, what a double bond looked like versus a single bond. And then this third form, which was covered in that part of chapter 6 we skipped, this ball and stick model gives us an idea of what it looks like in 3-dimensional space. Now, what we'll see as we go through this chapter is that there are even more representations than just these, but we'll start with these. Let's move on to the next least complicated. So now I've got 2 carbons. We call this compound ethane. we can see in ethane the beginning of what we would call a carbon chain. In these kinds of compounds, we will see that the carbons are going to be linked together with each other, and that hydrogens kind of fill out all of the remaining covalent bonds that are possible. And so that's how we end up with 6 hydrogens as opposed to 8. Because you might think to yourself, okay, well, if one carbon chain had 4 hydrogens, then a 2 carbon chain would have 8. I just double everything. Well, where that doesn't work is we have to consider that the carbon, the 2 molecules would have to link up with each other. And when they link up with each other, you're going to lose the ability to bond hydrogens because the carbons are going to link to each other rather than to other hydrogens. But we can see that the Lewis dot model, the expanded structural formula model, the ball and stick model all tell the same story. Just different ways of going about and doing it. We move into talking about alkanes. Alkanes are another way of phrasing organic molecules. So we're talking about hydrocarbons with all single bonds. Those are what alkanes are. Now, the example here is a 6 carbon chain. We call it hexane. But we can see the ideas that we were looking at in the ethane with the 2 carbons work out here as well. Carbon bonds to carbon first, and then we fill out the remaining bonds with these hydrogens. So for these carbons here in the middle, we can see they already have 1 bond, 2 bonds to other carbons, which means that they only have 2 bonds left over for hydrogen. Okay, so now we're getting into nomenclature here. What are alkanes? So again, they're hydrocarbons, carbons and hydrogens, and we only see single bonds. So carbon to carbon bonds are single, carbon to hydrogen bonds are single. We are going to end up seeing a continuous chain. So carbon bonds to carbon, bonds to carbon, bonds to carbon first. And we're going to use a naming system developed by the IUPAC, International Union of Physics, Pure and Applied Chemistry. The thing that they will all have in common, all of these compounds will end with the suffix ane. We already talked about 3 of them. Methane for 1 carbon, ethane for 2, hexane for 6. One really nice thing, one drawback, callback that we have is that those Greek prefixes that we learned for the molecular compounds all get reused once we start at 5. So the prefixes for 1, 2, 3, and 4 are different. We're not going to do mono, di, tri, tetra. They're going to be a little bit different. But after that, they're going to be exactly the same. Pent, hex, hept, oct, non, dec, which are exactly the same prefixes as what you had in that nomenclature that we did for covalent compounds. The complete list is here. So we want to focus in on these first four, because these first four are different. Now, we've already been introduced to the first two, meth and F, methane, ethane. So meth is 1, F is 2. The other two we've probably heard before. We just didn't know that that's what they were referring to. We've heard of propane from time to time. You know, some homes are heated by propane. You have a gas grill, you use propane in that. Well, it doesn't say on the tank, but that's what it is. It's a 3-carbon hydrocarbon. And butane, you have a lighter somewhere in your possession, somewhere in your home, it's got butane in it. Didn't know it. That butane just means it's got a 4-carbon chain. 4 carbons, 10 hydrogens. One other thing worth noting here. These formulas follow a pattern. And the pattern is, if I know the number of carbons, I can take that number, double it, and add 2 more, and that'll give me the number of hydrogens. Works for every single one of them. Carbon, or excuse me, methane, 1 carbon. Double it, it's 2. Add 2 more, it's 4. CH4. Hexane, 6 carbons. Double it, it's 12. Add 2 more, it's 14. Decane, 10 carbons. Double it, it's 20. Add 2 more, it's 22. So you can use that formula, and even if you don't know what the chemical formula is, if you know the prefix, or even if you just know the number of carbons that are in the chain, you can figure out what the chemical formula is. So that expands beyond even just these 10. You know, if I told you dodecane had 12 carbons in it, you could figure out that it had 26 hydrogens as well. Okay, so condensed structural formulas, the back half of this table. In a condensed structural formula, what we're doing is, instead of looking at these kind of formulas in the middle, the structural formulas, and writing them out all the way, showing all of the carbons and hydrogens and all the bonds that exist, what we're doing is we're condensing it down. And we're condensing it down by looking at each cluster around that carbon. So I would look at this carbon chain here and I'd say CH3, CH3. That would be the condensed structural formula, because the carbon on the left has 3 hydrogens around it. The carbon on the right has 3 hydrogens around it. And as I go, that's all I would do for all the ones in the middle as well. CH3, CH2, CH3. CH3, CH2, CH2, CH3. I could look at that full-on structural formula and just break it down into clusters based on what's on that carbon. That's called a condensed structural formula. And the whole point of it is to save space and to save some writing. We know that the bonding between carbon and hydrogen is always going to be a single bond. And we know that because hydrogen only has the 1 electron, it can only make the 1 bond. So with that knowledge, we don't need to show the bond between carbon and hydrogen. We know it's a single bond. So one of the things that we get into with organic chemistry is we get into a lot of assumed knowledge, stuff that based upon what we know in the past, what we've covered already, we can assume this and everybody makes the same assumption. We don't, and since it is assumed, we don't have to write it out fully. And this kind of thing is definitely going to be applied as we go through this chapter, as we go through the other chapters. So again, just highlighting the difference between expanded and condensed. Expanded shows all of the bonds. Condensed shows just the bonds that the carbon makes. Because again, we can assume that the hydrogens are going to be bonded with single bonds. Something we haven't had to consider yet is the idea of a conformation. Thus far, we haven't had to think about it because we haven't really drawn anything that had more than one center atom, more than one bond in it. But what we have to understand is that single bonds are capable of rotation. And so the atoms that are on the end here and on the end here, they are able to rotate. They're able to move around. And so what we can end up getting as a result of these different conformations is we can get slightly different structural looks. Now, in the cases of things like this, probably isn't going to make that big of a difference how it looks in terms of rotation. But if we start throwing in other kinds of bonding besides just single bonding, then those kinds of differences can be really important. So we've covered most of these kinds of representations. The one we haven't covered yet is what is called the skeletal formula. Now, the skeletal formula is one of those things that when you first get introduced to it, it's going to seem really weird and it's going to be kind of difficult to get your head around. Once you get used to it, you'll find that it's actually really useful because it takes the idea of the condensed structural formula and it condenses it even further. The skeletal formula is this guy right here on the bottom. And what is the assumption that we are making? Well, it's that we are looking at organic compounds. We know organic compounds are carbons and hydrogens. So if all we are looking at is carbons and hydrogens, this array of line segments is understood to be carbons and hydrogens. And how it works is this. Every single end and every single vertex, place where line segments meet, is where we would find a carbon atom. And so if I look at this, I can see, okay, I've got 1, 2, 3, 4, 5, 6 carbon atoms here in this compound. So that's the first assumption. Every end and every vertex where those line segments meet is a carbon atom. The other assumption that we make is that unless it is shown as different, we are going to assume that those carbons are saturated. And so they're going to have as many hydrogens around them as what their bonding would dictate. So that means on the exterior, they'd have 3 hydrogens. On the interior, they would have 2. And like I said, this is the part that is going to take probably the most getting used to, because everything else, we can kind of, okay, I understand this based upon what we were drawing in chapter 6. It's an expansion of those Lewis dot diagrams, but it's pretty easy to get my head around just the idea that there can be more than one middle. And I could even go to here and say, okay, I get it. Hydrogens are always single bonds. That makes sense. But when I go from chemistry with letters to chemistry without letters, that can be really abstract. It can be really hard to get your head around. So luckily, we're going to have a lot of practice with it. But it's going to be a little bit of a slog to get there. So work with me, ask questions. If you get stuck on something, stop me, and I'll try to explain it better. So here are, again, some different ways of representing butane, C4H10, and all of them mean exactly the same thing. Every last one of them. Why are we showing all of these different ways of drawing butane? Well, this is where that idea of conformations come in. What if, as that molecule's rotating, what if it turns this way instead of this way? What if they go outward instead of inward? They all mean the same thing. They're all going to behave in exactly the same way. And for the skeletal formulas, this one versus this one, it comes down to a preferential thing usually. Do you like to draw your skeletal formulas starting with an upstroke, or do you like starting them with a downstroke? That's the difference. Personally, I usually start with an upstroke. Does it matter? Not a lick. All right. Let's go through this together. Given the expanded structural formula here, let's figure out what the molecular formula is, what the condensed structural formula is, and what the compound's name is. So this is where some of those tricks should help us out a little bit. We know it's a hydrocarbon. We know it's saturated. How many carbons are in it? 1, 2, 3, 4, 5. So I have 5 carbons. So how many hydrogens should it be? Should be 12. Double it and add 2. 5 times 2 is 10, plus 2 more is 12. Now you could go through and count, double check. It is 12. From a condensed structural formula standpoint, again, all that we're doing is we're just collapsing these down to the individual carbons. So starting here on the left, this one would be CH3, then CH2, then CH2, then CH2 again, and then finally CH3. What is the name of this compound? Well, we got to put together our structure here. What is the prefix for 5? Pent. And all alkanes end with the same name, ANE. So this is pentane, pentane. Now, it doesn't ask us for this, but we're going to do it again just to kind of get some practice with it. What would this look like in skeletal form? So it's a 5 carbon. So the way that you do this is you're just going to make a series of line segments that are connected. And you just count. The only trick, the only thing that's weird is that you count from 2 instead of from 1. Because when you draw that first line, there's a carbon here and a carbon there. So that's 2 carbons. So 2, 3, 4, 5. That's my skeletal formula. If you want to start with a downstroke, it's the same idea. 2, 3, 4, 5. It'll take some getting used to. It'll be hard to see it any other way, especially once we get to the more complicated structures, though. All right. Condensed structural formulas for ethane and heptane. Ethane has how many carbons? 2. Six. 2 times 2 is 4, plus 2 is 6. So we'd be CH3, CH3. Another little tip here, the ends are always CH3s because they only have one thing that they're bonded to. And so if I only have 1 carbon bond, the other 3 have to be hydrogens. Heptane, what is hept? 7. So we start with CH3 and then CH2, so that's 2 carbons, 3, 4, 5, 6, and then the 7th one would be a CH3 because it's the last one in the chain. Well, I mean, we can. We don't need to write the formula necessarily because they're all going to follow the same pattern. It's going to be CH3, then a series of CH2s, then a CH3 at the end. And so really what's the most important thing is just counting and making sure you have the correct number of carbons. Now, again, just for kind of practice purposes, let's put on the skeletal formulas just to get some practice. 2 carbons, 1, 2. 7 carbons, 2, 3, 4, 5, 6, 7. So it's just segments. Up, down, up, down, up, down. Just remember that you're starting from 2, not 1. All right, questions with either of these? Okay, let's add a little bit layer of a complexity here. cycloalkanes. Cycloalkanes, anytime you see the word cyclo, think ring. The chain of carbons is going to attach to itself and make a ring. So cyclo, I guess more precisely, we call them cyclic alkanes. Again, we're thinking about the chain is connecting to itself. We're going to have two fewer hydrogens because now the chain's ends are connecting. So that's one extra carbon to carbon bond. So if we're thinking about formula, we don't do the +2 at the end. Two times the number of carbons. So if I have a 4-carbon ring, it's going to have 8 hydrogens. If I have a 7-carbon ring, it's going to have 14 hydrogens. And the reason is because this extra bond here that links the two ends of the chain would take away 2 hydrogen bonds. 2 bonds, 2 hydrogen. So what we see is naming structure is identical to what we were just talking about. We're just adding that additional prefix of cyclo to indicate that it's a ring. And so the parts that we're most interested in, parts that we care about the most from a naming standpoint, 3 carbons, so that's prop. So this is cyclopropane, this is cyclobutane, cyclopentane, cyclohexane. From a skeletal kind of standpoint, they just look like geometric figures. Triangle, square, pentagon, hexagon. But the interpretation of them is exactly identical to what we were just doing. The only difference is, again, instead of stretching out one long line of carbons, we now have a closed-in structure. Okay. Let's do some more naming here. Give the IUPAC name for each of the following compounds. All right. So with these, easiest way to go about them, count the carbons. So how many carbons are in that chain? I've got 1, 2, 3, 4, 5, 6, 7, 8. Prefix for 8 is oct. This is octane. For letter B here, with cyclical compounds, it doesn't matter where we start the numbering process so long as there's nothing else on them. When we start talking, this is gonna be more like Monday, when we start talking about compounds that have other things attached to the chain, then we've got to become more concerned with how we number. Bottom line here is it doesn't matter at this point. I've got 5 carbons, so that's pent. So if this was a chain, we would call it pentane. Since it is a ring, we're going to add that prefix to it. Cyclopentane would be the correct name.
This might be kind of obvious, but if it were the octane, like what's above, but it were in the ring, would we drop one of the O's?
Oh,
because it's like
cyclooctane.
Like
Actually,
with like pentoxide instead of pentaoxide.
That's actually a really good question. I don't think that convention applies with organics, because I mean, I'm just going, how would I pronounce it? I would pronounce both those. Cyclooctane as opposed to cyclooctane.
Yeah. I didn't know if we'd spell it with like OO.
That would be the only place where it would apply. Organic naming is more like, it's more like stacking. You know, you can almost think of like an organic nomenclature name is like a train. You've got the base, you've got the car, and then as you add more stuff to it, you just add more cars to the back of the engine, or in most cases to the front of the engine. All right, I want you to try these here yourselves. So we've got 4 different alkanes here. I want you to try to name them. I'll give you a couple of minutes to do it, and then we'll go through the results and see how you did. All right, so here are the answers. Maybe. There we go. So it really came down to, again, it's at this stage, it's all about counting. Just making sure that you've counted the correct number of carbons in the chain. And then for those, for B and for D, making sure that you put that cyclo prefix in front of the name to indicate that it was a ring as opposed to just a chain. Where we go from here is, again, we're going to add a layer of complexity. What if, instead of just having a chain, we had a chain that had some branches on it? We call those branches substituents. And as far as branching concerns, as far as substituents are concerned, there are a lot of different kinds. And so we're going to kind of ease into them kind of gradually here. So we'll start with just hydrocarbon substituents. And when it comes to hydrocarbon substituents, probably one of the most common kinds of ways of looking at this is through something called isomerism. Now, we've already seen the prefix iso used in other places. We use the word isotope to describe 2 atoms of the same element that had different looking nuclei because they had different numbers of neutrons. With isomers, it's kind of the same idea, but instead of looking at the element, we're looking at the compound. With isomerism, we are looking at 2 compounds, same chemical formula, but 2 different ways of structuring how it's all put together. So take a look at this example here. This is butane. Butane has 2 structural isomers. We have the chain version that we've already seen, 4 carbons all laid across. But we could also have a version where we have added a branch. And instead of one chain, we have a smaller chain with a branch on it. Both of them have the same chemical formula, but they have slightly different structures. And because they have slightly different structures, they're gonna have different properties in terms of their reactivity, in terms of their boiling points, in terms of a number of things. Question? They would also be named differently as well. Okay? Because now this is no longer what we would consider butane. This is where we need to start evaluating the chain itself. And so what we would look at this is we would say, oh, this chain only has 3 carbons in it now. This is a propane chain with a branch. And so, like I was mentioning to Olivia, when we start to do that kind of stuff, then it's like we're adding cars onto the front of the train. And so the technical name for this would be 2-methyl propane. And we'll get into the whys here in a minute. But no, when we start to branch out like this, it changes a lot of things. It changes physical properties. It changes the way that we name them. It changes their reactivities. There are a lot of things that are going to change. But technically, that if I was just looking at its chemical formula, it would look identical. And so one thing that we will see that is different is when it comes to that condensed structural formula, usually we will see this branching reflected in that formula somehow. Okay. If we were given a problem like this, draw the 3 structural isomers of pentane, C5H12. The way to tackle problems like this is to kind of work from the outside in. So what I mean by that is this. So the first structural isomer is the one that we've talked about thus far. CH3, CH2, 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 CH3. There I've got all 5 carbons. They're all in a perfect linear chain. What I mean by outside in is we're gonna start looking at, well, what if I take this one on the outside and bring it to the inside? And so how am I gonna do that? Well, I can't move it here because that would be the outside still. If I move this CH3, this CH2 is now the outer carbon. So I can't do that. I've got to move it further in. So if I do that, then I've got CH3, CH2, CH, because now I've got a CH3 hanging off of it as well. And this outside is now a CH3 because it's now the exterior. Because it only has one bond. So remember, to figure out how many bonds to hydrogen there are, I look at how many bonds to carbon it makes. So this one only makes the 1 bond to carbon, so it's got to make the other 3 to hydrogen. This one only makes 1 bond to carbon. The other 3 have to be hydrogen. This one only makes 1 bond to carbon. The other 3 have to be hydrogen. Why did this interior one change to CH? Well, it's got 1, 2, 3 bonds to carbon now. There's only room for 1 H. Okay, so that's the first alternative isomer. To consider the second alternative isomer, Got to do the same thing on the opposite side. Work from the outside in. Again, I can't put it on this one because that would be the same structure. I've got to put it on the one that's in the middle. So now this one is exterior, CH3. This one here in the middle is just carbon because it's got a CH3 above it and a CH3 below it and a CH3 to the side. If you count it up, it's still C5H12. But the three compounds are different from each other. And so this is what isomerism is. And isomerism is very, very common with organic molecules. Because you can see that when I have a whole bunch of single bonds to work with, there are lots of different ways, lots of different combinations that I could do to draw this out if I don't have to put them in a linear chain. And so with butane, there were 2 isomers. With pentane, there are 3 isomers. With hexane, there are even more. With heptane, there are even more. As that chain gets bigger, so do the number of possibilities. All right, let's look at the different kinds of alkyl substituents. All right, the most common, the easiest one is this first one, methyl. A methyl substituent, well, yeah, it's just a CH3 hanging off of an interior carbon. If I have a branch with 2 carbons in it, we would call that ethyl. If I have a branch with 3 carbons in it, we would call that propyl. Isopropyl, that one's a little bit strange. What you have basically there is a Y-shaped branch. So instead of the propyl group attaching to the end carbon, it's attaching in the middle carbon instead. So kind of looks like a fork in the road. The other kinds of common substituents, the halogens, all that we do with halogen substituents is we change that ending to O. So instead of fluorine, it's now fluoro. Bromine is now bromo. Iodine is now iodo. Chlorine is now chloro. And the key to numbering, so if we go back to what I wrote here, how did I know that this was 2-methylpropane? It comes down to you have to assign numbers to the carbons. The 2, that tells me where I find that group. It's on the second carbon. So what we end up doing is there are 2 different ways to number this chain. I can number it left to right, 1 through 5, or I can number it right to left, as such. Which one do I choose? Well, I've got 2 substituents here. I've got a methyl group here, and I have a chloro group there. Which combination do I use? Well, if I go with the top combination, I would have 2 and 3. If I went with the bottom combination, I would have 3 and 4 for the different groups. We're always going to choose the naming system that is going to give us the lowest numbers possible. And so that it means we're going to go with this combination here on the top as opposed to the one on the bottom. And so from there, we would name them in alphabetical order. So chloro comes before methyl. So we have 2 chloro, 3 methyl, and this is a 5-carbon chain, pentane. So a lot of things just went down there. Let's try to break it up into pieces again. Numbering. We're always going to identify the biggest chain, and we're going to number it. And there's 2 ways of numbering, left to right or right to left. We choose the numbering system that gives us the smallest combination of numbers. So we had 2, 3 or 3, 4. 2, 3 is the smaller combination. To put it all together, we name the substituents in alphabetical order, starting with their location. And so this is where I was talking about the train cars kind of idea. 2 chloro is a train car. 3 methyl is a train car. Pentane is a train car. The chain car is always the last one. The ones in front of it go in alphabetical order. So that's why the chloro is first instead of the methyl. It does not go in numerical order. It goes in alphabetical order by the name of the constituents, of the substituents. Question?
Okay, I understand like the 2, 3 being able to go with that one because it's smaller, but I don't understand where you got the 3 and 4.
If I were counting this bottom way,
Yeah.
then it would have been 4 chloro and 3 methyl.
Okay.
Because the chloro would have been on the 4th carbon in that numbering system as opposed to the 2nd carbon. Okay? All right, other questions with this example? Okay, draw the condensed structural formula for 3-bromo, 1-chloro, butane. Okay, so again, we need to think about this in, let's break it down into the cars. We've got butane. So we know we've got a 4-carbon chain. We know that at position 1, there's going to be a chlorine. And at position 3, there's going to be a bromine. Now, you can draw this whichever direction that you want. So this and that are technically identical. If I was numbering left to right or right to left. Since most of us go left to right because that's how we read, that's how we write, this is probably the most common way of doing it. Alexis? Well, on this one, if I'm counting backwards, then it's the third one. So you can kind of think of these as these are mirror images of each other. Okay, so from a condensed structural formula standpoint, we would just need to fill in the remaining hydrogens. So this would be our structural formula like that. If we wanted to make it condensed, CH2Cl, CH2, CHBr, CH3, but honestly, writing, you rarely see condensed structural formulas once you start getting into substituents. It's more likely that you're going to see them either written out in this full structural formula kind of way or in the skeleton. Because it can kind of get confusing pretty quickly about when you get into that. Like this. So again, it comes down to numbering here. 1, 2, 3, 4, 5. The numbers in purple are if I number left to right. The numbers in blue are right to left. There's only the one substituent there, the chlorine. So which number goes with the chloro? It's going to be 2. The reason it's going to be 2 is because I've got either 2 or 4 to choose from. 2 is the lower number. So this is 2-chloro. And so the chain is pentane because it's 5-membered. And so I would just put the 2 together. 2-chloro pentane. For this last one, 1, 2, 3, 4, 5. So purple numbers on the top, blue numbers underneath. 2, 3, 4, 5. My options, just like the first example, it's either 2, 3 or 3, 4, depending upon it's purple or if it's blue. In this case, the purple numbers make the most sense because 2 and 3 are going to be smaller. What kinds of constituent groups are these? Methyl. So this is a methyl group. This is a methyl group. More precisely, we could call this 2-methyl and 3-methyl. Here's the thing. If I have the same substituent on a chain, I don't name them individually. What I do is I attach a prefix to the substituent name. And I put the numbers together in combination with commas. So 2, 3, That's my combination of numbers. What do you think the prefix for 2 would be? It's di in this case. So one of the reasons why we use different names for the chains is so that they aren't confused with the multiplicity prefixes, which would be di, tri, tetra. So why did we change those? So that we could use the other ones here. So instead of meth, eth, prop, and bute, mono doesn't, we don't need mono, but it becomes di, tri, tetra. So those prefixes that you saw with nomenclature, this is where they show up. So this would be di, methyl, pentane. All right, one last important note. If we had a combination, so let's say that we had this chloro group on here as well. Prefixes do not change the alphabetical order. It would still be chloro, then methyl. So if we had, iodo and dimethyl, iodo would still go in front of methyl because I comes before F. So,
We were talking about this.
so don't use, when you're determining the alphabetical order, if there are prefixes involved, don't use the prefixes as part of that ordering. Use the root of whatever the substituent is. All right, that takes us through section 3. Technically, there is stuff from section 4 in that homework. It's not that much, and it's not that difficult to kind of put together on your own. What I'm going to do, I will put together a brief, maybe 10-minute supplemental tomorrow that covers this section to allow you to do that section of the homework if it gives you problems. But you should be able to do everything else because nomenclature is what's dominating this part of the chapter. Have a great weekend.